In this first video, we're going to get introduced to linear algebra through systems of linear equations. Okay, so this is section 1.1, Introduction to Systems of Linear Equations. Linear algebra is a powerful tool that can be applied in many contexts. We'll see throughout this course that can be connected to other areas such as economics, computer science, engineering, and other fields. Even within mathematics, it can be connected to analytic geometry, calculus, and statistics. However, at a basic level, linear algebra deals with studying how to solve systems of linear equations, and this is where we're going to start. Okay, so before we try to solve any kind of equation, let's go over some terminology, definitions, and notation. Often, math can be thought of as a language in itself, and so the terminology, definitions, and notations form the vocabulary and grammar of this language. And so to better understand things, we want to take care to understand the terminology. Okay, so when we're dealing with large systems, we're going to have to work with many variables in these situations. And so sometimes instead of introducing additional letters for all the variables like x, y, z, a, b, c, and so on, we're going to use a single letter we're going to use a single letter for the different variables, but then differentiate between the variables by using a subscript index instead. Right, so here I'm using the subscript index notation, where I'm using the letter x to denote each of the different variables, but then I put a subscript below and to the right of the variable x to differentiate between the different variables, right? So the indexing goes 1, 2, 3, 4, 5, 6, and so on, and it basically just tells you that x1 is the first variable, x2 is the second variable, x3 is the third variable, and so on. One thing to remember when using this index notation is that the number is just a labeling, again, to differentiate the variables, right? So the number itself is not used in any kind of calculation. So what do I mean by this? Right, so like for example, here I have some variable x3, right? So it's the third x variable in some kind of problem, and say it has a value of 4, right? So x3 is equal to 4, and say some part of a calculation, we have something that's given as minus 5 x3 squared, right? So you should read this as minus 5 times the variable x3 being squared. And so when you calculate this, right, so because x3 has the value of 4, we can plug in 4 into the variable, right? So the 3 disappears, right? Because again, the 3 is just labeling the x. It's not part of the calculation. And so when you calculate, it's just minus 5 times 4 squared. And from the order of operations, you do 4 squared first, which gives you 16. And then 16 times negative 5 gives you negative 80. So again, the subscript 3 is just labeling the variable. It's not part of any calculation. Okay, so that's the indexing notation. Again, I mean, when you're in a situation where you have 10, 20, 30, hundreds of variables, you're going to run out of letters, and so it's better to label them with these indexing numbers. Okay, so the next terminology we're going to discuss is what a linear equation in n variables looks like. So the general form of a linear equation looks like this. Right, so again, I'm using the indexing notation because I don't know how many variables there are, right? So you have the coefficients a1, a2, a3, an, and then the n variables x1, x2, x3 all the way up to xn, and the form is a1 times x1 plus a2 times x2 plus a3 times x3 all the way up to an times xn is equal to some constant b. So the different parts of the linear equation, right? So again, the x1, x2, x3 to xn are the variables. The a's are the coefficients, and the first term is called the leading term, and the coefficient of the first term is called the leading coefficient. So in general, for a linear equation, the coefficients can be any real number. They don't have to be integers. And the constant term can also be any real number. Again, it doesn't have to be an integer. So there are some rules on which operations can be involved as part of a linear equation and what makes it linear versus non-linear, right? So you can notice that you can't multiply the variables together, right? So the x's aren't being multiplied together, and then the power of x is always 1 in each of these terms. Some of the other restrictions that linear equations can't have products or roots of variables, and no variables involved in trig, exponential, or logarithmic functions, and so on. And as I said previously, variables only appear to the first power. Right, so trig, exponential, and logarithmic functions are they're called something called transcendental functions. So they're not linear. So one thing to understand is that these restrictions don't apply to constants, right? So you just can't have these things involved with the variables. So so what I've written here is some examples of linear versus non-linear equations, right? So at the top, these two are examples of linear equations, right? So the one on the left is pretty standard, right? So 5x minus 2y is equal to negative 16, right? So there's two variables, x and y, and the coefficients are 5 and negative 2, and then the constant term is negative 16. And then over here, it looks a little bit stranger, but this is still a linear equation, right? Because the variables x1, x2, and x3 are separated, and they all only have a power of 1, and they're not involved in any other function. So the cosine function here and then the square root function here are involved with constants and not the variables themselves. And so this is still a linear equation, right? So you can see that pi over 4 is just some number, and so if you take the cosine of that number, that's still just some other number, right? So this is just some number times x1, and then minus some number times x2, and then minus some number times x3, and is equal to another number, right? So, and pi is a constant, e is a constant, and then when you exponentiate it like this, the result is still a constant. Okay, so these two are examples of linear equations. And then down here, we have two examples of equations that are nonlinear. And you can have indicated what makes them nonlinear in these two examples, right? So in this term here, I have the variables x times y, x and y multiplying each other, right? So as we said, we can't have products of variables. And then here we have z appearing in the denominator, right? So you might think to yourself, okay, so it's written as z to the first power, but really if you think about it, when z is in the denominator like this, 1 over z is really just z to the minus 1 power, and the power for z is actually minus 1 in this case and not 1. So that also makes it nonlinear. And then in the second example here, we have the sine function and the exponential function applied directly to the variables x1 and x2. So this second example is also nonlinear. Okay, so we want to be able to tell apart what are linear equations or what are nonlinear equations, because again, linear algebra focuses on things that are linear, right? So these kinds of equations in general are simpler than nonlinear equations. Okay, so moving on. So at the bottom of this page, here, now instead of having a single linear equation, we're putting together several different linear equations to form what's called a system of m linear equations in n variables. So if you count going down, right, so this is the first equation, second equation, third equation, and then going down the mth equation, and then going across, you can count the variables 1, 2, 3, and all the way up to n. Right, so m equations in n variables. And this system is set up in what's called standard form. And it just means that when you're writing out the equations, you want to line up the variables so that they're together, right? So all the x1s appear in the first row, all the x2s appear in the second row, all the x3s appear in the third row, and so on. And then all the constant terms are lined up on the right side like this, right? So this is called standard form for a system of linear equations. One additional thing that's a little different now, because we have multiple equations, is the indexing for each of these coefficients. Right, so you want to be careful how you read the indexing, because we're going down going down the rows and also going across the columns. Right, so this 3 and this 2 are thought of as two separate numbers. Right, so this is what's called a double index. So sometimes it's written with a comma, and sometimes it's not written. Sometimes it's written without a comma, like it's written here, right? So, but if you want to make it a little bit less confusing, you can write it like a sub I comma j, like this, where you separate the two indexes with the comma, so that it's clear that they're representing different things instead of the number 32, right? So in the double indexing here, right? So if I have a coefficient a sub I j, the I is referring to that it's in row I, right? So, and then the j is referring to that it's in column j, right? So here a sub 3 2 is in the third row down and in the second column going across. Right, so A32, right, so you read it as A32, not A32. A32 means the coefficient in row 3, column 2, and not the index 32. Right, so in other words, it's in the third equation going down and then the second variable going across. Okay, so that's a system of linear equations. Okay, so now moving on to the third page of section 1.1, we come to our last definition in this worksheet. So here we talk about what it means to have a solution to a system of equations. Right? So a solution to a system of equations is a sequence of numbers that when you substitute it into the respective variables for each of the equations, that solution should satisfy all of the equations simultaneously. Right? So For example, here we have a simple system with two equations, 1 and 2, in two variables x and y. Right, so here I claim that x equals 2, y equals 0 is a solution to the system, right? Because if I take x equals 2 and y equals 0, plug it into the first equation, right? So you get 2 times 2 plus 0, which gives you 4, which satisfies this equation. And then if you take this again and you plug it into the second equation, you get 2 minus 0, which gives you 2. And so it also satisfies the second equation. So because both equations are satisfied, this is a solution. Whereas if you have something like this here, where suppose I take x equals 3 and y equals negative 2, right? So again, you try plugging it in, right? So if x equals 3 and y equals negative 2, what do you have? So you have 2 times 3 is 6. 6 minus 2 is equal to 4. Right, so it's okay for the first equation, right? So it works for the first equation. But now if I again take this and you put into the second equation, what do you have? So 3 minus a negative 2, which becomes 3 plus 2, which is 5 and not 2. So it doesn't satisfy the second equation, right? So when it works for one of them, but not the other, then it's not a solution, right? So this is not a solution. It has to work for all equations in the system. Okay, so that's what it means to have a solution. However, I mean, this example here, I essentially produce the solution for this system out of thin air, right? So in general, how do you actually, I mean, without guessing, how do you actually determine the solution? So that's where we move on to here, where we look at some examples. So again, we're dealing with simple systems where we have two equations in two variables, and we look at the different methods of solving these kinds of equations and what different kinds of outcomes can occur. Okay, so let's look at this first example here. Right, so I forgot to erase this down here. So let me just erase this real quick because I want to demonstrate how you solve it using these methods. Okay, so going back to the example, right? So I have a system of two equations. So let's number them, 1 and 2. And two variables x and y. So the first method we're going to do is to graph the solutions, graph the equations. And find the solution through the points of intersection, or point if there's only one of them. So the idea behind this method is that when you graph an equation, the points that form the graph are the solutions, are the x and y values that satisfy that particular equation, right? So the graph for the first equation will give the solution, all the solutions for the first equation. The graph for the second equation will give all the solutions to the second equation. And so to solve both of them simultaneously, it'll be the points that belong to both graphs, which would be the points of intersection. Okay, so to graph, because these are linear equations, to graph them, it's easier to put them into slope-intercept form. So we solve for y. So solving the first one for y, I first subtract the 3x over to the other side. So it becomes minus 3x. And then now to get the y by itself, I need to divide by negative 5. So you get y is equal to negative 3x plus 7 divided by negative 5. And then, right, so we're dividing the whole thing by negative 5. And so when you're dividing by a single term like this, you have to distribute the denominator, right? So the minus 5 goes into both terms. So minus minus becomes a positive 3/5 x, and then minus 7/5. Okay, so actually let me write the y in, right? So this becomes y equals 3/5 x minus 7/5. Okay, so that's equation 1. And we do the same thing for the second one, so I subtract the 2x over. So y equals minus 2x plus 9, and then now it's already in slope-intercept form, right? So the second equation is pretty straightforward. Okay, so now I have my two equations both in slope-intercept form, so now I can graph them. This is the graphing calculator I'm going to use, right? So it's the program WabbitEmu, which is an emulator for the TI-83 or TI-84 graphing calculator. If you go onto Canvas, I've posted instructions on how you can download this program so you can run the graphing calculator on your computer. So we'll be doing a lot of calculations with the graphing calculator, so it's good to practice using it and become familiar with it. Okay, so we're going to graph it, right? So I move it over so I can see y1, right? So this was y1, so I want to graph it, so I go into y equals, and then I enter in the two equations into y1 and y2, right? So the first one was 3/5, the variable x is here, minus 7/5. So this first one. And then the second one was negative 2x plus 9. Okay, so I graph the two of them. And you can see that the two graphs do intersect, so we have a solution here. And you can kind of make out the screen is kind of small, but you can kind of make out the hash marks. Right, so it's about 1, 2, 3, 4 over on the x, and then up 1 for the y. So it looks like it's at 4, 1. But in general, it's not good to eyeball where the various points on the graph is, because the resolution of the calculator is so low. It's very easy to be. I mean, how do I know it's exactly at 4 and not like 3.9 or something, right? So don't just try to eyeball the points like this. So actually do the calculation. So actually, how do I actually calculate the intersection point? So the graphing calculator does have a feature to do that, right? So if you look above the trace button in blue, it reads calc, right? So that's how you do calculations on the graph, right? So it's in blue, so I press second, and then calc, open up this menu, and what do I want? I want intersect, right? Which is the fifth option here. So I want to calculate the intersection. So it's going to ask you a few questions, right? So first curve, you can see the cursor is here and it's pointing to y1. So that's what I want as the first curve. I hit enter. So the cursor is a little bit hard to see, but I can move it over. You can see now the cursor is on the second graph and it says y2 here. So that's what I want. So hit enter. And then guess where the intersection is. I can move the cursor to, it doesn't have to be exactly on it, about where the intersection point is. And then hit enter. And you can see that it calculates the intersection exactly at x equals 4, y equals 1. So in general, the calculator uses various approximation methods to do these kinds of calculations. So I mean, sometimes you're not going to get the exact value, but most of the times it'll give you the exact value. But anyway, so we have the intersection point at x equals 4 and y equals 1. So I've already done this calculation previously, so I have a screenshot of that saved. So let me just put it into this this worksheet. Okay, so this was the graph. Whoops. Let me move it over here and make it a little bit bigger. So the intersection point right, so let me write in coordinate form. So x equals 4, y equals 1 gives the solution to the system. Okay, so again, it occurs here. Okay, so that's how we can use the graph of these linear equations to find the solution. Okay, so there are methods without using the graph, so you can actually just do it algebraically. So algebraically, as you remember from algebra class, there's a method called by substitution and by elimination. So let's try to do it in each way. Right, so let me just copy the equations again over here. Right, so the first one was 3x minus 5y is equal to 7, and the second one was 2x plus y is equal to 9. So substitution means you take one of the equations, you solve for one of the variables. So the second equation has a y by itself with a coefficient of 1, so it's easiest to solve for this y. So let's do that. So solve for y, and so you subtract the 2x, right? So it gives you y equals minus 2x plus 9, and then you take this and you substitute it into the other equation. Right, so substitute. So what do we get after substituting? So this goes in for the y, right? So everything else stays the same. So we have 3x minus 5 stays the same. And then now this y becomes this thing, which is minus 2x plus 9, and then equals 7. Okay, so then now after substituting, there's only one variable x, and I can just solve this as a single variable equation, right? So I distribute the minus 5, so I get 3x, and this becomes plus 10x minus 49 is equal to 7. I can combine like terms, so that's 13x. This 49 adds over to the right side, so 7 plus 49 is 56. And then I feel like we made a mistake here, because x should be equal to 4. I see where it is, right? So what did I do here? I need to distribute the 5, and then minus 5 times 9. What is that? That's not 49. That's 45. Okay, so yeah, be careful. Make sure you're not miscalculating anything. Okay, so that's minus 45, and then so I add it over. So 7 plus 45 gives you 52, and then finally you have to divide. So 52 divided by 13 is equal to 4. So x is equal to 4. And then again, now I know x, now I need to know y. So I substitute here. So what do I get? Y is equal to minus 2 times 4 plus 9. So that's -8. -8 plus 9 is 1, right? So y equals 1, which is exactly the same thing as before. X equals 4, y equals 1. I mean, it's the same system, so it should have the same solution. So here we've solved it by substitution. Okay, so finally, the other algebraic method is by doing it by elimination. Right, so let's again copy the system over. So 3x minus 5y equals 7. And then the other one was 2x plus y is equal to 9. Okay, so elimination means I need to cancel one variable, right? So let's cancel the y because they already have opposite signs, right? So I need to match the coefficients with opposite signs. So let's make this a 5. So I need to multiply the second equation by 5. This one already has the -5, so I don't need to change it. So I just multiply by 1. Okay, so now what do you get? So the first equation stays the same. The second one I multiply by 5, so I multiply everything by 5. Right, so that's what this means. So multiply everything by 5, so what do you get? So this becomes a 10x plus 5y equals 45. Okay, so this is my new system. This is a -5, this is a +5. Right, so now I add going down. Right, so then -5y plus 5y, that cancels out. Right, so that cancels. And again, I'm adding going down, so this is 13x equals 7 plus 45 is 52. See, this is the same equation as we had before, right? So, and we should be, because this is the same system, so we have to have the same answer. So I get x equals 4 again, and then to get y, again, I substitute back in. So 2 times 4 plus y is equal to 9. And then, so this is 8. So I subtract 8, so 9 minus 8 is 1, so y equals 1. Okay, so I also get the same answer by elimination. Okay, so we have these 3 different methods of solving systems of 2 equations in 2 variables. So it's a good idea to know how to do it all 3 ways, because sometimes it might be easier to do one way versus another way. Okay, so moving on to the 4th page of the section 1.1 worksheet, we have 2 more examples of systems of 2 equations in 2 variables. Let's approach them similarly to example 1. Right, so let's first do it by graphing. To save time, I'm gonna skip some of the intermediate calculations, right? So I add the 3x over. What do I get? Minus y is equal to 3x plus 3, and then I need to divide by -1 over to the other side, so it becomes minus 3x minus 3. And then similarly for the same way I solve for y, so what do I get? So 2y, I subtract the 6x, so minus 6x plus 1. And then I need to divide by 2. Everything's divided by 2, right? So this becomes a minus 3. And then 1 divided by 2 gives you 1/2. Okay, so because we're just following the same steps from before, I'm doing the calculations a little bit more quickly now to save time. Okay, so now I graph these 2 equations. So I go back to my graphing calculator. This is the graph from before, so I need to clear out these 2 equations. So what are the 2 new equations? So I have minus 3x minus 3, and then minus 3x, negative 3x, plus 1/2. And now if I graph them, what does it look like? So now what we have here is we have two parallel lines, and so there are no points of intersection. So let me insert the graph. So two parallel lines means no solution. So this system has no solution because there are no points of intersection. So that's what we see by graphing them. But you can see it using the other methods also, right? So what does it look like using some of the other methods? So let's do it by elimination. Right, so what is it? So minus 3x minus, so this is, so the first equation is minus 3x minus y equals 3. 6x plus 2y is equal to 1. So the y's have opposite signs, so I just need to match their coefficients. So let's multiply this by 2. This one stays the same. So multiplying by 2, you get minus 6x minus 2y equals 6. And then the second equation stays the same. So you get this. And then adding, going down, you see that this cancels because it's minus 6 plus 6, and then this also cancels, minus 2 plus 2, y. So the whole left side is 0, and I add the right side, it's equal to 7. Right, so whenever you have 0 equals some other number, means that there's no solution. Because 0 can't be equal to something else, right? That's impossible. Okay, so if you see 0 equals something else like this, that means that there's no solution. Okay, so continuing on to the third example at the bottom here. So again, this first do it by graphing. So what does it look like? So we solve for y. So subtract the 4x, right? So you get minus 8y equals minus 4x plus 9. And then I divide by negative 8. So negative 4 divided by negative 8 is 1/2. And then 9 divided by negative 8 becomes a negative, so 9 over 8. And what is this? So I subtract the x term, so you get minus 1.6y is equal to negative 0.8x plus 1.8. And then I have to divide by the negative 1.6. These are decimal numbers, so it's a little bit harder to do in my head. So let's just calculate that. So negative 0.8 divided by negative 1.6. So that gives you 1/2 or 0.5. And what is the other term? It's 1.8 divided by negative 1.6. So negative 1.125. Okay, so let's again graph them. So let's clear the last system. So what do we have? 1/2 x minus 9/8. And then the other equation is 0.5x minus 1.125. And it might not be obvious, but these are actually both exactly the same equation, right? Because 1/2 is the same thing as 0.5, and 9 divided by 8 is the same thing as, oops, this should be 1.125. Okay, so because they're the same equation, you'll see that when we graph it, it's the same graph for both of them. However, again, you shouldn't always just trust your eyes when looking at the graph like this, right? Because what if there's the possibility that one graph is like this, and then the other graph is a different graph, but it's just, say, off the screen, like going like this or something, right? So, so to see that they're exactly the same graph, I can use the trace button like this, right? So if you move the cursor, it will trace along the graph, right? So this is y1, right? So you see that it's moving, the cursor is moving along y1. If I press the up arrow here, now you see it switches to y2. And again, if you trace along the graph, it's exactly the same graph. So we do have the same graph here. Okay. So let me insert that graph. Right, so this was both equations give the same graph. Right, so the two lines are overlapping each other. So that means that there's infinitely many solutions, right? Because the entire line is a solution. Okay, so we have infinitely many solutions, and so in some situations, instead of just writing it as infinitely many solutions, we want to be a little bit more specific than that, right? So what exactly are the infinitely many solutions, right? So I need the infinitely many solutions comes from all the points that are on the two lines, right? So all the points that make up the lines. And so how do I describe the points on the line? So we can describe the infinitely many solutions using something called parametric notation. Right, so again, because they're both the same line, the entire line is the solution, right? So 4x minus, whoops, that's an 8y. 4x minus 8y is equal to 9 describes all solutions, right? So I can write it in coordinate form in the following way, right? So I introduce a parameter for t, and then I solve for x in terms of y. Right, so I plug in, I let y equals t, so I can plug in t for y, right? So so you get 4x minus 8 equals 9. I solve for x, so 4x equals 9 plus 18, and then I divide by 4, right? So x is equal to divide by 4, right? So 9/4 plus 8/4 t. 8/4 is just 2, right? So x equals 9/4 plus 2t. So y equals t, and x is equal to this thing. So you can write it as right? So x is that, right? So it's 9/4 plus 2t, comma, t. So again, this is parametric notation. Okay, so we can describe the infinitely many solutions using parametric notation. And then again, let's see what happens when you try to do by elimination what the solution looks like. Right, so by elimination, so what are the two equations again? So 4x minus 8y equals 9, and then 0.8x minus 1.6y equals 1.8. So I leave the first equation alone. The second one I can multiply by 5. So 0.8 0.8 times 5 is 4. Okay, so let's just do a calculation in my head to make it faster, right? So 1.6 times 5 is 8, so it becomes minus 8y, and then 1.8 times 5 will give me 9. So you see that both equations are exactly the same. So actually, let me make it have the opposite sign. So let's multiply by minus 5. So then this becomes a minus, this becomes a plus, this becomes a minus. And then now I add the two things, right? So everything cancels out. So what do we get? 0 equals 0. So when you see 0 equals 0 like this, that means that there's infinitely many solutions. And again, you can write the parametric notation this way. Okay, so moving on to the 5th page of this worksheet. So looking back at the 3 previous examples, we saw we have 3 different cases, right? So when you have one solution, no solution, or infinitely many solutions, those were the 3 cases. And the terminology is that when you have either one or many solutions, so if you have at least one solution, the system is called consistent, and if there's no solution, it's called inconsistent, right? So going back, this had at least one solution, so this was consistent. This had no solutions, so this was inconsistent. And then the first example here had one solution, so this was consistent. Okay, so that's just what consistent and inconsistent means. Okay, so moving on. So we dealt with systems of 2 equations in 2 variables, and in those cases the algebra of solving the systems wasn't too bad, but you can imagine if you have 3 equations in 3 variables, or any kind of larger systems. I mean, they could be mismatched, like 4 equations and 8 variables, or 7 equations and 5 variables, or something like that. You can see the algebra involved can become more lengthy and complicated. So there is a method of extending the elimination process for larger systems, and that's called Gauss-Jordan elimination, which we'll go over in the next section. But for now, we're going to see how to use the graphing calculator to handle larger systems. Right, so basically it's going to do the Gauss-Jordan elimination process for us, and I mean the calculation within the calculator does the Gauss-Jordan elimination, and then produce the solution. Okay, so how do we use the calculator for that? So in this example here, I have it's not that big of a system. It's just 3 equations in 3 variables, but the coefficients are all strange decimal numbers, and I mean trying to calculate by hand these decimal numbers doesn't look so fun, right? So so we're gonna put it into the calculator, but to have the calculator understand it, we don't want it in equation form, so we have to put it in what's called augmented matrix form. So basically what we do is we suppress the variables x, y, and z, right? So first you have to make sure that the equation is in standard form, right? So which it is, right? Because the x's, the y's, and the z's are all lined up. And so once it's in standard form, basically you just list the coefficients in all the correct places, right? So you can see that you have 120.2 here, 62.4 there, and then so on, right? So all the coefficients are in the correct places, and then the constant terms on the right side are in a separate column to the right, right? So all 12 numbers are in the exact same location. I've just suppressed the variables, and then the equal sign I've sort of denoted with this extra bar here. Okay, so this is called the augmented matrix, where you have the set of coefficients on the left and the constant terms in a column to the right. And in addition, right, so you can see that this matrix has 1, 2, 3 rows, and then going down 1, 2, 3, 4 columns. So those are the rows and columns. So rows go across like this, columns go down like this. Right, so it has 3 rows and 4 columns. So three rows, 4 columns, and so we call it a 3x4 matrix, right? So the first number is the number of rows, and the second number is the number of columns. Okay, so we put it into the calculator as a matrix. So I'm just going to demonstrate on this calculator here the procedure, but again, if you go onto Canvas, I have a separate worksheet that has the steps written out on how to do this calculation. Okay, so I need to enter in the matrix, right? So see above this button here, you see matrix, it's in blue, so I press second, and then matrix, and I need to edit a matrix. So I move the menu over to edit. They're all blank, so I just choose the first one, A. So I need to enter in the size of the matrix. It's 3x4, 3, and then this is 4. And you can see that now you can see the entries are made to the right size. And then now I just enter the entries one by one. Maybe I shouldn't have chosen all these weird decimal numbers. Now it's going to take forever to put it in, but in any case, I put them in. So 120.2. So they go across one by one, right? So, and then it's the next one going across. So that's 62.4. So, I mean, I'm entering a lot of different numbers into the calculator, right? So as you're entering these things in, be careful that everything is correct, because one wrong entry and that can screw up your entire calculation, right? So this one was 258.64, right? Make sure it's in the correct place. Now we're going to the second row, 56.8, then negative 42.8, then 27.3, then negative 71.44, 88.1, 72.5, negative 28.5, then 225.88. I did it kind of quickly, so hopefully all the numbers are correct. Okay, so I've entered in the matrix, so let's quit out of this screen. The matrix is full. Okay, so now I need to put the matrix in what's called row reduced echelon form, or RREF for short. Again, it's related to Gauss-Jordan elimination, which is discussed in the next section, so I won't discuss the terminology here. Okay, so row reduced echelon form. So I go back into the matrix menu, and in the second column, math, I go down until I see RREF, which stands for row reduced echelon form. I select that option, and now I need to tell what matrix to calculate it for, which was matrix A. So I go back into the matrix menu, and under names, the matrix I want is A, so I choose that, and so I press enter to do the calculation, and it gives me this matrix. Okay, so let me insert the screen there. I think this, make sure all the numbers matched up. So 0.8, 1.2, and then negative 2.4. Okay. So this was the row reduced echelon form, and let's put it back into equation form. Okay, so, and you can see that each row of the matrix corresponds to the equation, and the numbers are just representing the coefficients, right? So what does the first row say? The first column is for the variable x, and the coefficient is 1, right? So that's x, and then the coefficient for y is 0, the coefficient for z is 0, so that those variables don't appear for that equation, right? So the first equation just says x is equal to 0.8. And similarly, you can see that in the second row, y is a coefficient of 1, the others are 0, so the y variable is by itself, is equal to 1.2. And then finally, the last row is 0, 0, 1. This is for the z variable. So that says z is equal to negative 2.4. So I've staggered them so that they're in the correct positions, right? So the x column, the y column, the z column, right? So if you put it back into equation form, you can see it gives exactly the values for x, y, and z, which would be the solution for this system, right? So you can plug in the values for x and y and z and to check to make sure it's correct, but let's not do the calculation. It will take forever. Okay, so that's how we can use the graphing calculator to solve a more complicated system. Okay, so let's move on to the last page of this worksheet, where we're given this example, which is called coefficient design. Basically, you have a system of equations in two variables, right? So two equations in variables x and y, where the some of the coefficients are replaced by a parameter k. You shouldn't think of, even though k is a letter, you shouldn't really think of k as being a variable. It's an unknown parameter is a better way of thinking of it, right? And we're trying to figure out what k is. Okay, so basically the problem is, so you have these two systems, and you want to know what values you can put in for k so that the system of equations has a certain kind of solution. So in this problem, it's asking for what values of k does it have infinitely many solutions, and for what values of k does it have no solutions. So the way we're going to approach the problem is the following, right? So, I mean, it's not possible to graph it because there's, again, k, we don't know the number that represents k, right? So, going back to the previous examples, right? So we're going to use elimination, and depending on what form it takes, it'll tell us whether we have no solution or infinitely many solutions, right? So if you remember, the situation for infinitely many solutions was that the form was 0 equals 0, and for no solutions, the form was 0 equals to some number, right? So when you see 0 equals something, either 0 or something else, that's either no solutions or infinitely many solutions, right? So for infinitely many solutions, we want to look for the form 0 equals 0, and for no solutions, we want to look at the form 0 equals some other number. Okay, so, and then how we produce this form is, I mean, you can use either substitution or elimination. So what do I want to, yeah, let's just do elimination. Okay, so so 4x plus ky equals 6. I'm just copying it over here. So how do I do it by elimination? So let's say I want to match the y, right? So I need this has a coefficient of k. I would need a minus k here, right? So I would multiply this by times minus k. So this is my cursive k. So I multiply by minus k. So this becomes minus k squared x minus ky equals -3. And then the first equation stays the same. So that's 4x plus ky equals 6. And then I add going down. Right, so you can see that this is a ky, this is a minus ky. The same thing, opposite signs, so they have to cancel out. Right, so what do I have on the left? It's 4x minus k squared x. And then 6 plus -3 gives you 3. Right, so both these have an x, so I can factor that out. Right, so you get 4 minus k squared times x equals oh, I messed something up. So what did I mess up? So when I multiply by minus k here, what does that mean? Everything needs to be multiplied by minus k. Right, so minus k times k gives me minus k squared. Minus k times y gives me minus ky. And then minus k times -3 gives me a plus 3k. Okay, so now when you add going down, this should be 6 plus 3k. Okay. So now we get this thing. So where am I going with this? Okay, so going back to what we said before, we need the form to be 0 equals something. Right, so I need the left-hand side to be equal to 0. So how to get the left-hand side equals 0? Well, this whole thing becomes 0 if x is being multiplied by 0. Right, so I need, on the left side, I need the coefficient to be 0. Right, so we must have 4 minus k squared equals 0. And then from here I can figure out what k is, right? So you get 4 equals k squared, and taking the square root of both sides, k has to be plus or minus, right? Because remember, if you take the square root, you need the plus or minus. So square root of 4 is just 2. So k is plus or minus 2. Okay, so what this is saying is that if k is plus or minus 2, then the left-hand side is equal to 0. And you can see that's the case, right? Because if k is 2, you get 4 minus 4. If k is negative 2 squared becomes a positive 4. And so 4 minus 4 again gives you 0, right? So both of them produce 0 on the left side. But that doesn't mean that both of them are the solution, right? So we have to go back and check. Right, so each of them separately. Right, so k equals 2 and k equals negative 2. So what happens when k equals 2? So you have the left-hand side and the right-hand side. As you get 4 minus 2 squared times x. And then what do you have on the right side? 6 plus 3 times 2. So 4 minus 4 is 0, so that's 0 equals 12. So this is the no solution case. And then what happens when k is negative 2? So again, you check left-hand side versus right-hand side. So 4 minus negative 2 squared times x is equal to 6 plus 3 times negative 2. And again, this is just 4 minus 4, so that's 0. And this is 6 minus 6, so that's also 0. So this is the infinitely many solution case. Okay, so we see that the infinitely many solution case, that's this one, right? So this is the answer for A, and this is the answer for B. Okay, so that's example 5. So again, to save time, I'm gonna stop here. But as I said, it also works by substitution. Okay, so what do I mean by that? Okay, so let's copy the equation again. So let's copy this down. Right, so I can solve this for y, right? So y is equal to negative 3 minus kx, and you can take this, you can substitute it in for y here, then you're going to equation with just x, and then if you proceed, it'll look I mean, it might not be exactly the same, but it'll look like similar to what you have here with the x and the k. Okay, so you can continue from here. But again, I'm going to skip that calculation. But you can check it for yourself.